Welcome back to Computer Lessons.
Modern software applications rely on massive invisible data warehouses to process and organize digital information because standard file systems fail under heavy concurrent workloads. Large organizations require these robust systems to handle the complex data demands and high traffic of thousands of global users. When millions of users query prices or bank balances at once, organizations require a dedicated database architecture to maintain speed and data integrity. This layer provides an optimized engine for searching, sorting, and updating massive datasets in milliseconds while managing thousands of active connections. A database separates the logical data structure from the raw storage medium to maximize operational efficiency and prevent dangerous file locking conflicts in memory. This abstraction ensures multiple applications read the same information without causing data corruption or losing critical states during a system crash. Computer scientist Edgar Codd revolutionized data storage in the 1970s by inventing the relational model to replace rigid and inefficient hierarchical structures. Codd's mathematical approach provided a flexible way to link information without the need for predefined, fixed paths or complex physical filing. Codd proposed organizing raw binary information into interconnected logical sets, known today as two-dimensional tables rather than using a single massive flat file. A relational database management system constructs these tables using distinct horizontal rows and vertical columns to provide a clear mathematical framework. The vertical columns define the strict attributes of the stored information, such as customer names, identification numbers, or specific financial transaction details. Each horizontal row represents one distinct record containing the actual raw values corresponding to those predefined and rigid column attributes in Silicon. These relational tables enforce strict data integrity rules, known to engineers as schema constraints, to ensure the information remains clean and highly predictable. The database engine will reject any entry that violates the established data format to protect the software from processing errors and corruption. Every single table requires a unique identifier called a primary key to prevent absolute chaos and ensure that no two rows are ever identical. It serves as the master address for a specific piece of information within the engine, making every record accessible for retrieval. The true power of this architecture lies in establishing relationships between different independent tables through the use of shared and unique identifier codes. Engineers achieve this by utilizing foreign keys containing the primary key of another table to link customer records to their purchases. Database architects use a critical optimization technique known as normalization to eliminate redundant information and reduce the total storage footprint of the system. This process involves breaking down massive tables into smaller pieces to prevent errors during massive update operations involving millions of rows. Instead of storing a customer address next to every single order, the system separates it into a distinct and dedicated customer information table. Changing an address once in the main customer table automatically updates it for every related order record across the entire data warehouse. First normal form dictates that every column must contain isolated atomic values only to maintain searchability and strict relational integrity across the entire server. A single cell cannot store an array of multiple phone numbers because it would break the logical structure of the database. To interact with these complex relational structures, software developers utilize structured query language as a standardized and declarative programming syntax for data communication. It allows humans to talk to the database using a language that feels close to English instead of using raw binary. You do not write step-by-step processing loops to find specific data points because the database software handles the actual search logic and optimization. You declare what information you want the engine to retrieve or modify in the tables, and the system executes the command. The core operation within SQL is the select statement, which filters massive tables in milliseconds to pull a complete picture from different locations. Developers can join multiple distinct tables together inside a single query, leveraging the established foreign key relationships between the stored data points. The database engine calculates the most efficient execution path to return the merged dataset because scanning millions of rows one by one consumes memory. To avoid this slow search, engines use internal algorithms to predict the best way to retrieve the requested bits of information. Databases implement secondary data structures called indexes built using balanced B-tree algorithms to accelerate the speed of finding a specific piece of data. An index works like a book glossary, pointing the engine to physical disk sectors to skip irrelevant data during a query. While indexes speed up read queries by magnitudes, they introduce a performance penalty for write operations because the engine must update every index tree. Architects must balance read acceleration against this inevitable write latency overhead to ensure the system remains responsive under heavy production loads. Enterprise applications bundle multiple related storage operations into a logical unit called a transaction to maintain data integrity during complex, multi-step processing tasks. Relational databases enforce strict engineering rules known as ACID to ensure the system remains stable even during unexpected hardware or software failures. Atomicity guarantees that a transaction behaves as an indivisible operation that either succeeds or fails to prevent transactions from finishing halfway in the system. If a server crashes mid-transfer, Atomicity rolls back the incomplete operation to protect bank balances and prevent the creation of errors. Consistency ensures that any given transaction transitions the database between valid states, while isolation guarantees that concurrent transactions execute without interfering with one another. These rules prevent users from buying the same item at the same time during high-traffic sales on the web. Durability dictates that once a transaction is committed, data changes are permanent even if the system loses power or the hardware fails. Storage engines achieve this by writing details to a separate log file before applying binary changes to the actual tables on disk. As internet traffic exploded, scaling these rigid relational databases became an immense engineering challenge because they rely on vertical scaling and expensive server hardware. This physical limit forced developers to find new ways to distribute data across multiple machines using a brand new storage paradigm. To solve the horizontal scaling problem, software engineers developed NoSQL architectures that sacrifice strict ACID properties to achieve infinite scalability across massive clusters. This allows companies to handle petabytes of data by using thousands of cheap commodity server computers instead of one giant machine. Document databases store records as flexible JSON documents instead of using fixed rows and columns to accommodate rapidly changing software applications and social feeds. You can nest arrays and objects inside a single document, eliminating the need for complex and slow joins during data retrieval. Key value stores provide ultra-fast in-memory caching by bypassing the slow mechanical hard drive entirely to load session tokens and user data without any delay. This architecture is the secret behind the instant response times of the largest websites and most popular mobile applications today. In our next technical episode, we will explore file systems like NTFS and FAT32 to understand how these managers organize bits on a drive. This topic will complete our understanding of how data is physically stored in silicon and on spinning magnetic platters in hardware.
Understanding these diverse storage architectures reveals the immense complexity behind every simple web search and every click on your favorite social media application. Do you think strict relational databases or flexible distributed systems offer better long-term security and reliability for your personal data? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching and keep learning.